Chapter 38, Photons and the Quantum Mechanics. Question: What did Albert Einstein win the Nobel Prize in Physics for? Special relativity, general relativity. Swedish Academy. The Nobel Prize in Physics 1921 was awarded to Albert Einstein for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. Chapter 38, Photons and the Quantum Mechanics. Our learning goals in this chapter: to consider the fundamental constituent of light, the photon; to study the ejection of an electron by an incident photon, the photoelectric effect; to understand how the photon concept explains X-ray production, X-ray scattering, Compton scattering, and E+E pair production; to interpret light diffraction and interference in the photon picture; to introduce the Heisenberg uncertainty principle, photoelectric effect. Photoelectric effect. Interesting fact: blue light striking cesium causes the cesium to emit electrons. Red light does not. Einstein's explanation: light comes in photons. To emit an electron, the cesium atom must absorb a single photon whose energy exceeds the ionization energy of the outermost electron in cesium. A blue photon has enough energy, a red photon does not. Photoelectric effect. Photoelectric effect apparatus. Dunnett and Phys 274L. Photoelectric effect master equations. Maximum kinetic energy of the electron is the energy from the photon minus the work function phi. Stopping potential V0. The current at which the photoelectron current stops. Photon quantization master equations. Where H equals 6.63 by 1034 J/s. Question: How can we express the photon energy in terms of the photon wavelength? On. Use F equals C/lambda, recall C equals lambda F. Question: What is the photon momentum in terms of wavelength or frequency? But wait, the massless photon has momentum? From special relativity. Einstein's explanation of the photoelectric effect. A photon carries a discrete amount of energy. For light of frequency f and wavelength lambda, this energy is E equals hf, or E equals hc lambda, where h is Planck's constant 6.626 times 10⁻34 J/s. This explains how the energy of an emitted electron in the photoelectric effect depends on the frequency of light used. See figure on the right. The momentum of a photon of wavelength lambda is P equals h/lambda. Photons are quantized. The photoelectric effect. Examples. This is also called phi in the master equation. For the P effect. The photoelectric effect. Many applications. Photons enter the scope and hit a plate ejecting electrons, which then pass through a disk with millions of tiny channels. The current in each channel is amplified. Night vision scopes. Solar cells. By the photoelectric effect, photons excite electrons into the conduction band. Solar cells. Photon quantization. Example. A laser pointer with a power output of 5.00 mW emits red light, lambda equals 650 nanometers. A. What is the magnitude of the momentum of each photon? Since light is quantized, we only need the frequency or wavelength for this problem. Could also use E equals hc/lambda. B. What is the energy of each photon? Photon quantization. Example. A laser pointer with a power output of 5.00 mW emits red light, lambda equals 650 nanometers. B. How many photons does the laser pointer emit each second? Calculated in A. How do we calculate the number of photons per second with this information? Huge, but each photon has a very small energy. Photoelectric effect. Example, how to determine H. For a particular cathode material in a photoelectric effect experiment, you measure stopping potentials V0 equals 1.0 V for light of wavelength lambda equals 600 nanometers, 2.0 V for 400 nanometers and 3.0 volts for 300 nanometers. A. Determine the work function, phi for this material, and then the value of Planck's constant h. Question. Suppose we plot V0 versus f, frequency. What does the graph look like? The vertical intercept is phi/e equals minus 1.0 volts. The slope of the graph is he.